Okay. I think what I'm going to do is I'm going to start over this world and see if I can't comprehend it a little bit better. Start at level 1. Right, so proofs like 2 plus 2 equals 4 and a plus b plus c plus d plus e equals e plus d plus c plus b plus a are very tedious to do by hand. In Algorithm World, we will learn how to get the computer to do them for us. Alright, so delete that before I get a chance to read it. Having to rearrange variables manually using commutativity and associativity is very tedious. We start by reminding you of this. Add left commutative is a key component in the first algorithm, which we'll explain, but we need to prove it manually. Remember that you can do precision commutativity by rewriting things like rewrite add commutative BC. And remember that a plus b plus c means the a and the b are being added first. Okay, so we just need to get the b and the c to change places. Wait, what does this one do exactly? Is the proof that a plus b plus c is equal to a plus b plus c. No, so this doesn't change the order the numbers are in. That changes the order in which we do them. We need to add commutativity. And right now, all that's doing is it's putting the b first, but we want to put, or no, we do want to put the b first, but we're putting the b and the c first. If we do what it recommends doing and type b, c, then what happens? And we just change the order of b and c. But I don't think that's what we want to do. But we want to change CA now that we've wait. Wait, why doesn't that work? Or maybe we need to, because it's B plus C is one like unit together, and we need to make it C plus A, and then we can use commutativity to, so we need associativity first. And now A plus C are one together. And then we can use rewrite, add commutative A and C. There we go. Okay. Whoop, whoop. In some later worlds, we're going to see some much nastier levels, like a plus 1 plus b plus 1 equals a plus b plus 1 plus a plus b plus 1. Brackets need to be moved around, and variables need to be swapped. In this level, a plus b plus c plus d equals a plus c plus d plus b. Let's forget about the brackets and just think about the variable in order. To turn a plus b plus c plus d into a plus c plus d plus b, we need to swap b and c, and then swap b and d. But this is easier than you think. with add left commutative, which is the one we just proved. Where is it? Oh, right here. It's the pink one. Is the proof that A plus B plus C is the same as B plus A plus C. So we trade these two places, whereas add right commute, A plus B plus C becomes A plus C plus B, in which these two, the ones on the right, that makes sense. The ones on the right, this one switches the ones on the left. Okay. Start with repeat, rewrite, add associative to push all the brackets to the right. So what is add associative? Is the proof that A plus B plus C equals A plus B plus C. So like it says, it pushes the brackets to the right. So repeat, rewrite, add associativity. So before it looked like that. So we had A plus B on its own, and then added to C plus D. And now we have C plus D plus B plus A. Oh, ah. And then it didn't do anything to the other side. A plus C plus D plus B is still A plus C plus D plus B. Okay, I kind of don't like how it tells you what to do. I feel like I don't get the feeling of learning it if you just tell me the steps. One of the things that I liked about the main game in this was that, you know, you have to figure it out. And even though it was hard, it felt, I don't know. Anyway, well, what do I think I need to do next? Just by looking at it, B, D, C, and D, C and B. So we need to switch the B and the C, and then we need to switch. Yeah, we switch the B and the C, and then we'll just have to switch the D and the B at the end. And it says to use left commutative, which makes sense because left commutative will switch. Won't it switch the C and the D? Isn't that what it'll do? Unless we specify BC. I guess we can specify. But if we're specifying, then what's the difference between... This just switches two of them around. Why can't I just use that? B and C. And that doesn't work. Why? What is the difference between this and left? The left version of it. I suppose it's probably because you can't switch the place of B and C, because B is already in this relationship with D. C plus D is one thing together in brackets. And then, yeah, so it won't let them swap. But left commutative is the proof that A plus B plus C becomes B plus A plus C. Right, it switches these two. Okay, yeah, that makes sense. Do I need to specify that I want B and C, or is If I don't specify, I wonder which ones it will select automatically. Add left commutative. Which ones did it select automatically? The first ones. Okay, that makes sense. It did these two. But we don't want to do those two. We want to do B and C. Okay, now what? Now all we want to do, now it should just be commutative. Rewrite, add commutative, which is what it says to do. Like, come on, I could have figured that out. Why are you... I don't know. I think that's what was getting me frustrated last time, is it just kept telling me what to do, and I kept, just following the instructions step by step, and I never felt like, I didn't feel like I was learning anything, like I was with the main ones, where it gives you very limited hints. And then all of a sudden, you get to here, and it's just telling you what to do. And then you get to the end, where it doesn't tell you what to do. And you're suddenly totally lost. Where was I? Level 3? No. I was not on level 3. I was on level 2 then. We're only on level 2. Okay. And that swapped a whole bunch of stuff that I don't want to do. In fact, it took C. Yeah, it switched the places of this A and this whole thing. But all we want to do is change B and D. And that's it. There we go. Now let's use automation to perform it automatically. Oops. Hang on a sec. Okay, I'm back. Okay. Lean's simplifier simp is rewrite on steroids. It will rewrite every lemma tagged with simplify and every lemma fed to it by the user as much as it can. So every lemma tagged with it. This level is not a level you want to solve by hand. Get the simplifier to solve it for you. So we have D plus F. Yeah, we have just a whole bunch of letters all the way through H. So in order to use simp only, and first we're going to use add left commutative, which is going to take, what exactly is the order here? Is it totally random? Is it randomly scrambled on this side? We have a plus b plus c. It's all in alphabetical order on this side. This is a plus c plus b, a, b, c, d, e, f, g, h. It seems totally random. This is the proof that a plus b plus c becomes b plus a plus c. So we're going to switch around every So what did that do? This d plus f went in here. So I'm wondering how this is different than just saying repeat rewrite. If I just do that, didn't do anything. So what did this do? All this did was, we have that g plus e plus b becomes g plus e plus d. What's going on? Add left commutative is going to take every one of these and switch them around so that the one outside the brackets is inside the brackets. So starting at the beginning, this g plus e will get moved outside of the brackets, and this h plus a plus c will get moved inside of the brackets where the g plus e is. So what we should see, h plus a plus c plus b. Yeah, h plus a plus c plus b. That's exactly what we get. And then this g plus e will now be outside here. This d plus, wait. What happens to the g plus e? G plus e plus b. Okay, so plus b, it's at the very end here. Oh, I see. G plus e is being switched with this entire block. This whole thing will trade places with G plus E. So we'll end up with D plus F at the beginning. Wait, no. No. I was, okay. Oh, no, I see it now. I get it. Only one thing happened. So all of this counts as one block, and they all traded places with just these two. So G plus E got moved to the beginning. And then everything else is the same, ending with plus B. Okay, that's all that happened. All these... Wait. Yeah. Okay, yeah. All of these, this entire block, traded places with this G plus E. That's all that happened. Now, why can't I repeat this? Is there just nothing to do a second time? No, there is. Oh, but it just switches it back to the way it was before. So now I understand. If I tried to repeat it, it would just loop forever. Yeah, maximum recursion depth has been reached. I assume that means it's redoing it over and over. So we can't do that. So then what is simp? Simp is different from rewrite somehow. Whoops, what did I do? Simp. First of all, you can use simp without simp only. Simp by itself and simp only looks like the same thing. I'm not sure what the only adds. I don't know what that does to anything. But anyway, what does this do? This is different from rewrite. We've got G plus E at the beginning. And we've got A plus C. So how did this one work? So I believe all rewrite did was take the first blocks that it could find and switch them around. But what simp is doing is it's taking each block. Let me see if I can figure out what it's doing exactly. Whoops. Okay, it doesn't like that. So H, what happens to this block? H plus A plus C, is that still intact on the other side? H plus A plus D plus F plus C. H plus A plus D plus F plus C. So this D plus F somehow got in between here. So based on what's highlighted, I would expect this G plus E. I wonder why it's highlighting the individual G and E and not the plus. Whereas here it's highlighting the plus. So D plus F stays together, but this G and E. But G and E do end up together. That B stays at the end. Add left commutative. What should we expect to see? This D plus F plus C. Oh, no, wait. This D plus F. A plus B plus C. So this D plus F is one block, and it's going to trade places with H. Or with A. D plus F. The D plus F trades places with A. That's what's happening here. D plus F, H plus D plus F plus C. So it's taking this block here and trading places with the A here. And then I think the whole thing is trading places with the G plus E. Yeah, that makes sense. So it's doing two things. We're taking this D plus F and trading places with this A, and then we're taking that whole thing and trading places with this G plus E, and that's how we end up here. Okay. And then it wants me to just add commutative. So what will that... And that's going to be different than if I simply repeat, rewrite, add commutative. Yeah, that's... Well, we run into the same problem where it keeps doing the same thing over and over again. Just doing it once, all that happens is this G plus E, A plus H plus D plus F plus C, A plus H plus D plus F plus C. Okay, so all that did was trade these two's places. But if I do it as a simp, wait, that solved it without even having to... I don't understand how simp solved it. Even if it did get them all in the right order, why don't I still have to use RFL? Whoa. What happened now? If I do it on a second line, everything falls apart. Well, I messed up everything on both sides. But for some reason, if I put this on the same line as the first one, we win. But I don't... One does not truly win until they understand how they have won. What happened? Add commutative, all it should do is trade the places. Okay, G and E trade places. A and H do D and F trade places? Are D and F still next to each other? Yes, they are. D and F. D and F are D and F are still on the same side relative to each other, so they didn't switch places. D plus F and D plus F. So that's something. Now D plus F plus C, I suppose the C is now before them, so the C switched sides. Right, D plus F plus C became C plus D plus F. And then H plus this whole block. I suppose that swapped places and now H is after? No, H is not after, H is still before. A plus H and A plus H. A and H didn't move at all either. So E and G switched places. A and H. Oh no, wait, that B at the very end trade places with this whole block. So the G and the E traded places, the B traded places with this entire block, and then the C traded places with traded sides and became C plus D plus F. And on this side, H was at the end, and now it's at the beginning. And then A and B, A plus B are still together and on the same side of each other. But C, or it's A, B, C, D, E, F, G, H. Right, so if you imagine quotation marks, whoa, what is happening? If you imagine not quotation marks, parentheses around these ones, it's a plus c, a plus b first, plus c, plus d, plus e, plus f, plus g, plus h. And then it totally switches around, a, b, c, d, e, f, g, h. It's just reversed parentheses. But it never switched this first one, which I don't know why. Why didn't it? I thought it... Now to simp only, if we add the only, it's the same thing. I do not know what the difference between simp and simp only is. Simp seems to work perfectly fine by itself. Simp only seems to do exactly the same thing. So I don't know what that means. And I don't know why running this in one line should be any different from doing it in two separate lines. But it must be. It must be different. It must have something to do with the way simplify works. It must treat it differently when you tell it to do multiple things in one line than if you run simp multiple times. It's a little difficult though, because I can't, if I click here, no matter where I click now, it's completed. Oh wait, no. Yeah, see, I can go back to the very beginning, but I can't see what happened before and after I added this. And I still don't understand why it completed. Why it didn't just, make both sides match, and then I could use RFL. I don't understand why it was able to finish without me using RFL. What would have to happen here to get it in alphabetical order? The B would have to trade places with this entire block. And then we'd have A plus B. The C would have to trade places with the H. And then D, A, B, C, D, E, A, B, C, D, D, and the F would trade places. I don't know. I don't know if I can understand this right now. I might just need to move on. But yeah, it solves it, and I don't know why. And I don't know what the difference between simp only and simp is. But I guess we'll keep going. Okay, well, that's pretty basic. Here you can make your own tactics in Lean by running this code. If we were actually using Lean, then I guess that would be the code we used to make a tactic. This code was used to create a new tactic, simp add, which runs simp only, add, it runs what we just did last time. No, that's different. This is different than what we ran last time. Try running simp add to solve this level. It will solve arbitrary goals of the form A plus B plus C plus D plus E. equals E plus D plus C plus B plus A. Okay, so this is the exact same problem as we had last time, right? That was level 3. Add left commutative, add commutative. Yeah, that's different than this. Add associative, add left commutative, add commutative. Or the second part is the same thing, but then they added associative. They added add associative, which is will rearrange the parentheses for me, I guess. But I guess it'll do those 3 things. It'll rearrange the parentheses, it'll push all the parentheses to the left, or it'll do its thing, and then it'll finish, and that's that. Let's now move on to a more efficient approach to questions involving numerals, such as 20 plus 20 equals 40. We now start work on an algorithm to do addition more efficiently. Recall that we defined addition by recursion, saying what it did on 0 and successors. It is an axiom of Lean that recursion is a valid way to define functions from types such as naturals. I'm not sure what that means. A valid way to define functions from types such as the naturals. Okay, let's define a new function predecessor from the naturals to the naturals, which attempts to subtract 1 from the input. The definition of this is predecessor that 37. I don't know what 37, why is there a 37 here? I don't know why that is. We cannot subtract 1 from 0, so we just return a junk value. Oh, is that what is 37 the junk value? I guess, because it's saying the predecessor of 0 is 37, which is junk, I guess? The predecessor of 0, we cannot subtract 1 from 0, so we return a junk value. As well as this definition, we also create a new lemma predecessor-successor, which says that predecessor of the successor equals, the predecessor of successor n equals n. Let's use this lemma to prove successor, what was this? Injective. That's what it stood for, successor injective. The theorem which Peano assumed as an axiom and which we have already used extensively without justification. Start with, backwards, so we're going to turn A into the predecessor of a successor. backwards arrow. We have to specify which one. And now it's successor A dot predecessor, which I guess is the predecessor of successor A. Then we will need to, we have the hypothesis that successor A equals successor B, which means that A equals B, which is what we had down here. But we have to prove it rewrite H, and now the predecessor of successor B equals B. And we have our new lemma, this one, which says that the predecessor of a successor is just the number itself. So that's all we need to do here. Pred success. And now B equals B. There we go. Nice, we've just proved the successor injective. Now let's prove Peano's other axiom, that successors can't be zero. We define a function is zero thus. Is 0, 0, true? Is 0 successor, false? So is 0 is a function, and if it's 0, then it's true, and if it's a successor, then it's false. We also create two lemmas, is 0, 0, and is 0 successor. And so this is the proof that is 0, 0 is true, and is 0 successor is false. Let's use these lemmas to prove that successor NE0, Peano's last axiom, to prove this, Peano's last axiom, is the proof that M does not equal N implies that successor of M does not equal the successor of N. I don't know what the NE stands for, but anyway. Where was I? Actually, we have been using 0 NE successor before, but it's handy to have this opposite version. Oh, well, I already did this level, so of course it's unlocked already, now that I'm going back. I was wondering why it was unlocked. This isn't the one we're doing right now. We're doing successor NE0. So when I did this level before, I had unlocked 0 NE successor, but not successor NE0. So this is the one that we're going to prove, and it's unlocked because I already did it yesterday. But it's handy to have this opposite version too, which can be proved in the same way. Note, you can cheat here using 0NE successor, but the point of this world is to show you how to prove results like that. Right, I could just switch them around and then I could cheat using symmetry, right? Sim switches it around. And then all we would have to do is use... Nope, that's the one. This one. 0 does not equal. Wait, no, we don't... It's not a rewrite, it's an apply or something? There you go. And that's the cheaty way to do it. The cheater's way to do it. But we'll do it the other way that it wants us to do it. If you can turn your goal into true, then the trivial tactic will solve it. Trivial will solve the goal true. Okay. Start with intro H, remembering that x does not equal y is just notation for x equals y implies false. So intro, what is that? What does that do again? If the goal is that P implies Q, then the intro H will introduce H, the hypothesis P, as a hypothesis. It'll introduce P as a hypothesis and change the goal to Q. Okay. Sure. Yeah, okay, I kind of get that. So this, which is notation for x equals y, implies false. So what this would do here is it would make xy our hypothesis, or it would make x equals y our hypothesis, and then false would become our goal, which is a little hard for me to wrap my head around. That your goal is the word false. You have to prove that false. I'm not sure I understand that. But anyway. So when I do this is the successor of A does not equal 0, which is the same as the successor of A equals 0 implies false. So when I run this, we will get a hypothesis that says the successor of A equals 0, and our goal will be false. So intro H. Yep, successor of A equals 0, and our goal is false. So we have to prove that the successor of A equals 0 is false. We're going to change that false into true. Start by changing it into is 0 successor A by executing that one. Right, we have this one here. This is the proof that is 0 successor A equals false. And we have 0. We're going to do it backwards with the backwards arrow. And that's going to change our successor A equals 0 into wait, we're not changing this. It's not telling me to say at H, right? I would have to have at H in order to change the hypothesis. But we're going to change the goal, which the goal is just false. So, I'm still a little bit confused. Backwards arrow, we're going to change A, or this, we're going to change the successor of A equals, we're going to change false. Oh, false is 0, successor A equals false. So we're going to do it backwards and turn false into is 0 successor A. If I had more false statements, is that a thing you could do? You could just turn a false statement into any other false statement? Like if I had the statement, I don't know, pigs fly, and then I turned that into, if I used the backwards arrow, or no, I turned pigs fly implies false, and then I used this, I could transform the term, I could change do pigs fly into 0 equals a successor. Those are equivalent mathematically because they're both false. So you could turn any false statement into any other false statement. They're all like interchangeable. Huh. Anyway. I think I watched like a computer file video, the YouTube channel Computer File, where I think he was doing something like that. And now I'm thinking maybe that's what he was doing, something like that. Anyway, just is 0 successor. And we're going to do it to A. First of all, why is there a question mark? M.7. No idea what any of that means, but if we press it, oh, that's A. So the successor of A dot is 0. See if you can take it from here. So we have the successor of A dot is 0. And we have successor A is 0. So I can turn... So I turned that false statement into the statements the successor of A is 0. Which is impossible because 0 is never a successor. But we have the hypothesis that the successor of A equals 0. And now we have is 0, 0. What am I trying to prove now? Wait. Trivial. We use the trivial tactic. Because that's true. It is true that is 0, 0 is a true statement. Oh, but I think we need to turn it into a true statement first, right? If I try trivial, No, that does work. But I also could have gone, what happens if I 0, 0? Now the goal is true. And then if I same thing. It was a true statement either way. It didn't matter how you displayed it. Okay. What next? Is this a level I haven't beaten yet? Level 7. Yep, that's where we stopped last night. Out of frustration. Okay, what's happening now? Here we begin to develop an algorithm which, given two naturals, A and B, returns the answer to does A equal B? Here is the algorithm. First, note that A and B are numbers and hence are either 0 or successors. If A and B are both 0, return yes. If one is 0 and the other is the successor of n, return no. Okay, yeah, that makes sense. If A equals the successor of m and B equals the successor of n, then return the answer does m equal n. Our job now is to prove that this algorithm always gives the correct answer. The proof that 0 equals 0 is RFL, reflect. The proof that 0 equals 0 is RFL, right, that's the first one. If A and B are both 0, then return yes. The proof that 0 does not equal successor is 0 NE successor n, and the proof that the successor of m does not equal 0 is the opposite, 0 NE successor NE 0. The proof that if the proof that if our hypothesis m equals n, the proof that if m equals n, then successor m equals successor n is rewrite H, our hypothesis, and then reflect. This level is a proof of the one remaining job we have to do. If A does not equal B, then the successor of A does not equal the successor of B. Start with contrapose H. To change the goal into its contrapositive, namely a hypothesis of successor m equals successor n and a goal of m equals n. Wait, is that a new tactic that it gave me? Yeah, contrapose. If you have the hypothesis A does not equal B and the goal C does not equal D, then contrapose H replaces the setup with its so-called contrapositive hypothesis. C equals D and the goal AB. Okay. So it's just going to switch these around, right? This will become the hypothesis, and this will become it's gonna change both of these equal sign of both of these does not equal signs into equal signs, and then the hypothesis will be successor m equals successor n, and the goal will be m equals n. So contrapose contrapose H. Oh, I know this. This is the symbol for not, but it's the first time we're seeing it in this game. The little dash with the down means does not. Oh, okay, so it did do what I thought it would change the does not equal sign into an equal sign, but instead it just added a not symbol at the end. Now what do I do? Wait, we just need... this one. If the successor of A equals the successor of B, then A equals B. Nope, it doesn't like that. Wait, is it a rewrite? I never remember. No, it doesn't like that. Pretty sure it's apply. You have to use apply to use this one. No. Do we need to turn not this statement into? Do I need to get this into an equal sign? I don't know how to do that. Wait. I think I didn't. That's different. I didn't see that exclamation point. I thought it was just being excited. Start with contrapose. No, exclamation point is part of it. So contrapose usually, I guess these kind of mean the same thing. Not. You're just adding not. But here we're actually changing the does not equal sign into equal sign. Can you take it from here? Nope, if you try contrapose exclamation point H again, it will take you back to where you started. Okay. Now can I use this? What will it do? That's what it will do. And then we simply need to use H and RFL. There we go. And now we have proven that if A does not equal B, then the successor of A does not equal the successor of B. Oh boy. Implementing the algorithm for equality is, implementing the algorithm for equality of naturals, and the proof that it is correct looks like this. Code, code, code. 0 and 0 is true by the show that 0 equals 0 reflect. The successor of m and 0 is false because m does not equal 0 because of this. The other way around is the same. 0 and the successor of n is false because of the opposite. Successor ne0, 0 ne successor. Successor m and successor n match. If they match, if they are the same thing, then m equals n is true because the successor of m equals the successor of n. We can show that. There's the proof there. And if it's false, we can prove that it is false because the successor of m does not equal the successor of n. And successor ne successor, which is our new one that we just proved. This lean code is formally this lean code is a formally verified algorithm for deciding equality between two naturals. I've typed it in already behind the scenes because Because the algorithm is formally verified to be correct, we can use it in lean proofs. You can run the algorithm with the decide tactic. Decide will attempt to solve a goal if it can find an algorithm which it can run to solve it. Oh wait, so am I just... Oh, that's it. It automatically picks the correct algorithm. You can read more about the decide tactic by clicking, yep, that's what I did. Decidable EQ. Okay, number 9. We gave a pretty unsatisfactory proof of 2 plus 2 does not equal 5 earlier on. Now give it a nicer one. Are we just... That's it. That's our nicer proof. What if I mess around? That's not... The exclamation point is not doing anything this time. Okay, so that's I'm pretty sure that's all it wants us to do, is decide. Woo, let's go. We just use our algorithm that we got. Congratulations, you've finished Algorithm World. These algorithms will be helpful for you in Even Odd World when someone gets around to implementing it. Is that not a thing yet? No, it doesn't look like it. It's a thing. Alright, cool. We did it. We did it. We did it. Alright. Let's move on to Advanced Addition World. See if I can get a few of those done tonight. Alright, in Advanced Addition World, we will prove some basic addition facts, such as x plus y equals x implies y equals 0. No, sorry, I can't read apparently. X plus y equals x implies y equals 0. X plus y equals... Yeah, okay, that makes sense. The theorems proven in this world will be used to build a theory of inequalities, that's the less than or equal to sign. Or is it the greater than or equal to sign? I can't remember. Click start to proceed. Is it the first thing? The first thing is smaller than the second thing. But I don't remember if that's... It would be x is less than y. I think this would be less than, and then the other way around would be greater than. Anyway. In this world, I will mostly leave you on your own. Add, write, cancel ABN is the theorem that A plus N equals B plus N implies A equals B. Okay. Wait. Oh, add, write, okay, that's the one we're proving right now. A plus N equals B plus N implies A equals B. Yeah, okay. That makes sense. But how do I solve it? What do I do? A equals N, B equals N. Am I overthinking this, or should I use induction? Because if I can prove that N is 0, I feel like we're getting somewhere. If I induction N, the implies we'll just repeat, rewrite, add 0. And now A equals B implies A equals B, which is true, but that's not, we don't, no, that doesn't work. How do we, surely we have a tactic to prove that, is it trivial? No, it's not trivial. Surely A equals B does imply that A equals B. But that's not, what did I, what do we need to find? Oh, there we go. There we go. I get it. Oh, we're not done. We're using induction. Induction. Wait, do I need to be using induction now that I think about it? What if I just introed H? Intro H. Now we're getting somewhere, I think. Wait, our goal is that A equals B. A plus N equals B plus N. We would need to get rid of the N, which we can only do if N is 0. Like, what about... That looks better. We have this new hypothesis. We have our new induction hypothesis, which says that A plus N equals B plus N implies A equals B. We're back in this scenario. How do I get rid of the successor? How do I make successor N into N? I simply must get it out of the way. Successor B is the successor of A plus B. There we go. Repeat it for everything. I believe that could work. There we go. Repeat that as well. Okay, now we just have plus ones in there. Can I use my induction hypothesis now, or does it not work because there's a plus one? No, it won't work. What if I... Oh yeah, that worked. Now we have the same thing on both sides. We can get rid of this implies by simply intro H, and now B equals B. The successor of B plus N equals the successor of B plus N, and B equals B. Oh, we're not done? What's happening? That can also... Oh no, that's A plus... that's A plus N equals B plus N. There we go. Now, are we done? Wait. What's happening? What's happening? B plus N equals B plus N. It just keeps swapping. What's going on? We have this on either side. Intro H. h gave us, that successor of b plus n equals the successor of b plus n. No, but it's, I don't know what's happening. We use reflects, and then all of a sudden our hypothesis, no, a plus n equals b plus n. This came down a plus n does equal b plus n, which implies a b. No. Well, I'm a little confused about what's going on here. Maybe I'm doing things in the wrong order. Maybe I should have introed h at the very beginning. And then we do that. And we rewrite with h. Oh, we can get rid of this one now, because we introed h at the beginning. Now we have a equals b. We use that to turn it into b equals b. We reflect it. Now we have trouble. We have to prove that a equals b. What? We used induction, and now the induction has come back to haunt us. Are you sure there's no way to just prove that a plus n equals b plus n? Can I use the decide tactic? Will this algorithm help me? Possibly. It did not. That didn't do anything. We have multiple hypotheses going on. We have a plus n equals b plus n implies that a... Do I need to intro another hypothesis? No. Maybe. I don't know. piano. You know what? I might be done for now. We finished one world, which is good. And I felt like I understood it much better than I did yesterday. I was getting real frustrated yesterday. But, yeah. I guess we'll continue with this tomorrow. Alright, goodbye.